Hi, welcome. All right, today we are going to look at this decay reactions worksheet. So you'll need your chemistry reference tables, right? We're going to need table N and maybe table O and of course the periodic table. Okay, so our first task is to define natural transmutation, which I already did for you in my kindergarten handwriting with my stylus on this computer. So natural transmutation is when there's one reactant and it spontaneously decays. Spontaneous means it just happens all on its own, right? It doesn't have to be forced to happen. You do not add anything together on the reactant side. So the clue is one reactant. So if you see here, I have one reactant. So if I look at this equation, I have gold with a mass of 198, right? The arrow means change, and it's releasing this little funny looking thing here. And I need to figure out what element this is going to change into, right? Because this is what transmutation, the prefix trans means change, mutate into something else, right? So change into something else. The element gold is going to change into something else when it gets rid of this whatever from its nucleus. So how do I figure out what that whatever is? Well, first of all, I'm going to look at table O in my reference tables, and I'm going to find a match to this particle. So I'm going to go over to the reference tables, and I am going to go to table O, other way. So when I go to table O and I take a look around, I have a match to this particle. I think it was this one down here, right? Was it a positive one down there at the bottom? Let's go take a look again. Oh, negative one, sorry. This is why you have to read really carefully. So it's not going to be this one, right? We're going to see this one. So then what is that particle? That is the beta particle. And if I release a beta particle, we're going to say that is called beta decay. Okay, so beta decay in my kindergarten handwriting. Okay, so now that I know that this is a beta decay, so I'm just going to write that down over here. This is a beta decay. And I know that because it produces a beta particle. So in order to become a more stable element, this gold has got to get rid of this extra baggage, this particle from its nucleus. So I need to figure out a top number, a bottom number, and a symbol. So the top number is 198. The bottom number over here for gold is going to be number 79. And how do I know it's 79? Ooh, 79. Let's make that look prettier. All right, so how do I know that that's going to be 79? 79. I go over to my periodic table, and I'm going to find gold. AU, give me your gold, number 79, right? So there we go. That's number, we've got our gold, which is number not 179, but 79. There we go. 79. Okay. So then gold is 79. The law of conservation of mass says our top numbers and bottom numbers have to be equal. So if I have, let's switch colors. Okay, let's go with a blue. So if I have a 198 over here, that means the top number on the other side plus 0 has to equal 198. Well, obviously, with a 0, I'm just going to need a 198. All right, so now the bottom numbers have to be equal on both sides. I have a 79 over here and a negative 1. So then I have to figure out what number plus negative 1 is going to be equal to 79. Well, then that's going to be 80, right? Because 80 plus negative 1 equals 79, right? It's not going to be 78 because a 78 plus a negative 1 would be a 77. So actually your atomic number is going up in this case. So then now I have a top number and a bottom number. All I have left to do is figure out what symbol this is. What element does gold transmutate into spontaneously? So then I need to go to my periodic table and I need to find atomic number 80, which is right here, mercury, Hg. So now I'm just going to copy that symbol, Hg. And I'm not going to copy down the mass from the periodic table, just the symbol. All right, so now let's take a look at our next one. I have francium and I have a change. There's only one reactant, so it's a natural transmutation. And then I produce this funny looking thing. So how do I know what kind of decay this is going to be? I'm going to go to my reference tables and I'm going to find table N and there, oops, not table N, table O. And I'm going to find that funny looking particle. And it looks to me like, according to this table, that funny looking particle is the alpha particle. So now I'm going to go, and since this is an alpha particle, this is going to be an alpha decay because it produces an alpha particle. So then francium is unstable. It's going to eject an alpha particle from its nucleus. That's what radioactivity means. It means it's emitting particles or rays from the nucleus. So then I need to figure out the bottom number for francium, right? They don't give it to you all the time because you have it on the periodic table. So there's no need for them to type that in. Plus, it's also very difficult to type in a superscript and a subscript on top of that element. So francium is down here, right? It's number 87. All right, so we're going to put an 87 down at the bottom. So I have an 87. So now I have a 220 and a 4. So in order to figure out the top number of this element that francium is transmutating into, what number plus 4 equals 220? Or the shortcut to that is take 220 minus 4. So is that going to be 216? Did I count on my fingers correctly? 216, 217, 218, 219, 220. Yep, counted on my fingers correctly. Okay, so now I have the bottom number. I have an 87 on the left-hand side, and I have a 2. So what number plus 2 will add up to 87? Or 87 minus 2, because that's the same thing, right? So that's going to be 85. Am I right? 85, right? 86, 87. So now I go back to my periodic table and I figure out what is element 85. So I'm going to go back to my periodic table. Element number 85, of course, means I'm going to have to go all the way to the other side over here. Where's number 85? There's number 85. Astatine, AT. I'm going to copy down that symbol. AT. Okay, so notice that this is not the same mass as astatine on the periodic table, right? Because these are isotopes, right? We have radioactive isotopes. All right, so now on our next one. So if I look at my next one, I'm over here, I have a 32He and I have an H. So in this case, I'm trying to figure out what particle is going to be released. So I know that hydrogen has an atomic number of 1. I got that from the periodic table. Top numbers have to be equal on both sides. Bottom numbers have to be equal on both sides. So the top number on this side, I have a 3 and I have a 3. So in order for the top numbers to be equal, my top number has to be a 0. So now the bottom numbers, I have a 1 and I have a 2. So what number plus 2 will equal 1? Yes, a negative 1. So now all I have to do is figure out what has a top number of 0 and a minus 1 at the bottom. So this is not going to be an element in this case. So I'm not looking at the periodic table. I'm actually going to be looking at my particle table, table O. So which one has the negative 1 on the bottom and the 0 on the top? That's right, our beta particle, right? Very careful. Your positron is a positive 1 at the bottom. The beta particle is the one in this case. So then I'm just going to write the symbol for a beta particle. So you can use the E or you can use that funny looking B, which is just basically the Greek letter beta. Okay, so if I look at the next one, I have iron and it's got this funny looking thing. So this means that this is a radioactive transmutation, right? Iron is going to change into something else by getting rid of something from its nucleus. So what is that getting rid of from its nucleus? I have a 0 and a positive 1 and that funny looking B. So that's the beta with a 0 and a positive 1. So in this case, this is the positron. And we don't call it positron decay for some reason. I really don't know why, but we call it a positron emission, right? So emission. When something emits, it means giving off, right? So an emission is something that's given off. Okay, so top numbers, bottom numbers. I believe the atomic number of iron is 26, but I'm going to check the periodic table so that you check the periodic table, right? Fact checked me. 26. Good job. I was right. Okay. Bottom number is 26. So a 2, 6. Okay. So maybe let's make that 2 look a little bit better. It's still not good. Kindergarten 2s. Okay. So top number is 53 on the left. I have a 0 on the right. So my top number must be 53, right? Because they have to be equal on both sides. So I have a 26 over here and a positive 1. What number plus the positive 1 equals 26? That's going to be 25. So now I go to the periodic table and I see what is element number 25 right next to iron, right? That's going to be manganese right here. Oops, click that, right? That's going to be manganese. There we go, manganese. So I just do Mn. All right, so now I have a little bit of a different situation in this natural transmutation. I don't know what the original element is, right? So we call the original element the parent nucleus, and then we call what it turns into the daughter nucleus. Okay, so top numbers and bottom numbers have to be equal on both sides. So what is 235 plus 4? Do it on your fingers if you have to, or you guys have a calculator, right? So then what is it going to be? All right, so it's going to be 239, right? 239, right? Because that's going to be 235 plus 4. Okay, so top number is 239. Now the bottom number, I have a 2 and a 92. So 92 plus 2 is 94. So that means that my bottom number will be a 94. Now I just have to figure out what is the atomic number 94. So I'm going to go back to my periodic table. I'm going to find 94. So it might take you a little while. Oh, I found it. Okay, 94 down there. Pu, plutonium. Okay, so plutonium undergoes what kind of decay will this be? It's going to be alpha decay because it's releasing an alpha particle. So notice that the mass decreases by 4, the atomic number decreases by 2. In the beta decay, which is a little bit weirder, right, the mass stays the same, the atomic number increases by 1. Okay, so let's keep moving on. Now we're going to define artificial transmutation. So transmutation is still going to mean the same thing, right? Trans means change, right? So then we have change, and then we have mutate, change into something else, change into something else, but it's artificially. So if natural was spontaneous, artificial will be non-spontaneous. Non-spontaneous. And then in this case, I will have 2 or more reactants. So notice I have 2 reactants that makes this artificial. I have 1 reactant that makes that natural. Okay, natural, one thing changes. Artificial, we need to add things together, right? So this is like, particle collisions, right? This is, fancy nuclear stuff. Okay, so same rules apply, right? If I have to figure out what is this transmutating into, top numbers and bottom numbers have to add up to the same number on both sides, right? Law of conservation, matter, energy, and charge, always conserved. So I need a top number, a bottom number, and a charge. So I believe the atomic number of nitrogen is 7, but let's fact check. Nitrogen is 7. Okay, so then 7. And so now I have a 7 plus 2 for the bottom. So then 7 plus 2 is what? So that's 9, right? So I've got 9 on the bottom to keep track of. I have a 1 over here. So then what number plus 1 equals 9? Okay, do we agree? 8, right? 8 plus 1 equals 9. Okay, so now I have a 14 plus 4. So that's a total of 18 on that side. And I have a 1 over here. So what number plus 1 equals 18? 17. So now I just have to figure out what is that atomic number 8 going to be. So let's go back to our periodic table. Atomic number 8, oxygen. And there's oxygen. Notice that the mass is not 16 because this is an isotope of oxygen. All right, our next one. We have aluminum, and it has an atomic number of 13. Feel free to fact check me on that periodic table, but I know this one. Okay, so I have a 13 on the bottom. And so now over here, I have a 15. So what number is going to be added to 13 to get up to 15? Right, we're going to have a 2 on the bottom. Okay, so now I have a 23 so far on the left side. I have 30 plus 1, that's 31. So then what number is going to go on the top? All right, so I want you to think about that. Do we agree that's an 8? Or is that too much? Is 23 plus 8 equal to 31? Yep, it does. I just did on my calculator to prove myself right. Okay, so bottom number 2, top number is 8. What do I do? What's atomic number 2? Find the periodic table, find number 2. Oops, gotta do that. And atomic number 2, helium, all the way up here at the top. Okay, so then helium, right? Remember, this is an isotope of helium. Okay, next one. All right, so we have lithium. I'm just gonna make this go up higher. Okay, I have lithium, which is, I believe, atomic number 3. So atomic number 3. So I have a 3 plus 1. That's going to be equal to 4 on the bottom. I have 6 plus 2. That's equal to 8 on the top. So then my numbers on the other side have to also add up to 8 on the top and 4 on the bottom. So I already have a 1 on the top over here. So then I'm going to have a 7 because 7 plus 1 equals 8. So then over here I have a 1, right? And I need to get to 4. So then it's going to be a 3. So then atomic number 3, lithium. Okay, so now I want to define fission. Okay, so fission, right? If I have a fissure in the Earth's crust, what does that mean from earth science? You probably remember that. So then fissure just means a split. So this is where we split atoms. All right, so fission is when you split an atom, right? And what kind of atom? Only ones with a large nucleus, or atoms plural with a large nuclei. So if something is splitting, so then basically what you're looking for is you're looking for this, right? So in a multiple choice question, you're always looking for this uranium thing. And I believe this is going to turn into krypton. Let's see if I'm correct. So atomic number is 92 for uranium. So I have a 92 on the bottom. So right now I have a 56 and I have 3 times 0. 3 times 0 is 0. So I have a 92 and I have a 56. So I do 92 minus that 56, and that's going to tell me that my bottom number is going to be a 36. So now for my top number, I have a 235 plus 1, right? That's going to be a total of 236. Right now, I have 141, and I have a 3 times 1, right? So that's a 3. So 141 plus that 3 is a total of 144. I'm just going to jot that down over here, 144, right? Just jotting myself some notes. So if I have a 144 over there on the right-hand side, I have to get that up to 236. So I do 236, and so then it's going to be 92, right? Because 92 plus 144 is going to be the 236. So then I find atomic number 36, and I find where's 35, 36. There's that krypton, right, that I told you about. Okay? Krypton 36, right? This is the example in almost every single question that is asking you to identify fission, right? They're looking at uranium. Uranium is going to get bombarded, right? That means hit really hard with a neutron. So what happens is then it splits into two new elements, right? Fission, produces three more neutrons that now can attack and bombard more uraniums, right? So that's called a chain reaction. All right, so now we have the opposite of fission, which is going to be fusion. So fusion is fusing together. So this isn't where we split atoms. This is where we join atoms together. But we're not joining the whole atom. We're talking about the nuclei, right? So nuclear chemistry is all about the nucleus. So then as we go up to the top, I'm going to freeze that. This is what you're always going to see for fusion. You're always going to be seeing hydrogen plus hydrogen in some form. But you might see different top numbers, right? Different isotopes of hydrogen. But if I add 1 plus 1, my bottom number is 2. Over here, I have a 0. So this is going to turn into something with a 2 on the bottom. So I have 3 and 2 is equal to 5. So over here, I have a 1. So I'm going to do a 4 because 4 plus 1 is equal to 5. So then I'm going to go check my periodic table, and I'm going to find that atomic number 2 is helium. So then this is fusion, right? So fusion is basically we're doing hydrogen making helium. We're joining together, right? I'm adding two things, I'm making and transmutating it into something else. So then this is also can be a chain reaction because now I have those neutrons. Okay, so if I'm talking about energy, I just want to quickly go over to a blank page over here. I'm going to click on my little writing tab. So then nuclear reactions produce a large amount of energy, really large energy. Much more, oops, yucky handwriting today. So very much large energy that's going to be greater than any kind of chemical reaction. But why? Why are nuclear reactions producing so much more energy? The reason is E equals mc squared. Okay, you've seen that before. You're like, oh yeah, that's Einstein's formula. But now we're just going to kind of get into just a little bit of exactly what does this mean. So this just means that energy is equal to mass and then times, this is just a number. So it's the speed of light, which is just a number. That's an of, not an ox, squared. So what does this mean in terms of energy? So this basically means that this mass gets converted to energy. So mass gets converted to energy very efficiently with no carbon dioxide. So nuclear energy is a rather clean form of energy in terms of greenhouse gases. Okay, so if I go back to my nuclear equations, and I just want to say just a little bit, because you can't talk about nuclear chemistry without talking about nuclear bombs and nuclear power. So then we had, in World War II, we had two different nuclear bombs. We had Fat Man and Little Boy. So then one was a completely fission reaction, which took uranium and split uranium. But then you have one that's called the H bomb, or the Little Boy, which is smaller, which combined the fusion with the fission. And we had a fusion reaction, right, which produces a neutron and then can start hitting some uranium to produce 3 more neutrons in chain reaction. This one is the largest energy production, right? Fusion. It's the hardest to do because you really need extreme heat and you really need extreme pressure. And the only place to get that kind of extreme heat and pressure is the sun. The sun is a giant nuclear reactor of a burning hydrogen gas forming helium. And then obviously the helium can then do other things. Okay, so then this also goes back to the Big Bang Theory. Okay, so hopefully I demystified the decay reactions a little bit. And one more note up at the top of the screen over here. What type of decay is this? Is this natural or is this artificial? So let's examine two reactants. This is going to be artificial. Oh my goodness. I really should invest in a new stylus, shouldn't I? Okay, so this is artificial. So I'm just going to do art for short. And what kind of artificial? Is this normal? Is it fission? Or is this fusion? Well, I've got a neutron and I'm hitting this target nucleus and it looks like I'm making all of this stuff. So then this is splitting. This is not joining together. This looks like this is breaking apart. So then this is fission. Okay, all right. Until our next video, I hope you enjoyed. Make sure to join the Google Classroom, ask questions, join our Zoom meetings. Until our next one, bye.